and holography.
Great. Can you hear me? Right. So first of all, I'd like to thank the organizers. It's my first time in Wrocław and also my first time at this conference. So it's really great being here. So yeah, so I was asked to give some sort of review talk on all things non-Lorentzian, maybe is the broadest way I can define it. And I will assume that non-Lorentzian geometry is something you haven't seen before. And so the plan of my talk is not to get very technical, but to just give an overview of where you encounter these objects, why they're useful, and why we study them. And in order not to just only say general things, and because it's a string theory audience, at some point I will switch topics about halfway through, and we'll talk about non-Lorentzian string theory, in particular non-relativistic strings. So that's kind of the plan for the talk, and please interrupt me if something isn't clear, and we can keep it a lively discussion. Also, people in the back, is this too small? Is this legible? It's okay. Okay, I'll try to write big. If I don't manage it, please tell me if you can't read it. Okay. So personally, I encountered non-Lorentzian geometries for the first time because I was studying boundaries of non-ADS spacetimes. And I will explain in a minute why ADS is special for many reasons, but from the point of view of non-Lorentzian geometry, ADS is special because if you write ADS in a Vielbein basis, and you go to the boundary and say Pfefferman-Graham coordinates, the Vielbeine all blow up at the same rate. And that means that, and I will make this more explicit in a minute, that the geometry induced on the boundary is still Lorentzian. You have a bunch of Vielbeine on the boundary that transform on the local Lorentz transformations. But as soon as you only modify it ever so slightly, they will not blow up at the same rate, and that it gives rise to these non-Lorentzian geometries. But I'll give two examples of that later. You may also encounter them by looking at hypersurfaces inside a Lorentzian metric that isn't either time-like or space-like. So for example, null hypersurfaces is a thing that you may have heard before. They have this thing called Carroll geometry associated to them. So if you look at black hole horizons, they are an example of a Carroll geometry. Future null infinity, which isn't really a hypersurface, but it's a hypersurface in the unphysical space where you do the Penrose compactification, becomes Carrollian. You may also encounter non-Lorentzian geometries if you zoom in near singularities. So like a space-like singularity of a Schwarzschild geometry, the light cones become, they kind of collapse to a line, and you get ultra-local physics. Again, it's associated with Carroll geometry. But you may also encounter it because you did it on purpose. For example, you make approximations of GR, like the post-Newtonian approximation. As the word says, you are starting with Newtonian gravity, and you can make Newtonian gravity diffeomorphism covariant using non-Lorentzian geometry. In that case, it's something called Newton-Cartan geometry. Again, I'll give an example of this later on. So to just draw, let me draw the Schwarzschild Penrose diagram, just to make this point a little bit more clearly. Whenever something special happens in this diagram, so suppose you reach the singularity, or you focus on the horizon here, or you are approaching future null infinity, something non-Lorentzian happens to the metric. And in this case, you get every time you get an instance of Carrollian geometry. So this is a very simple way of motivating why these geometries are quite relevant, even just in an ordinary GR context, not only if you're interested in approximations. So this gives some background why non-Lorentzian geometries are important in general relativity. But they're also important in field theory in very general terms. Let me switch writing device. So in field theory, most QFTs are not Poincare invariant. And so if you're interested in condensed matter physics, you will not have Poincare invariant theories in general. Or you may have a Poincare invariant theory, but you want to approximate it in particular, and that will play an important role when we discuss strings. You can approximate it near some BPS bound. What happens if you zoom in on BPS bounds is that you get non-relativistic physics for the excitations that are just above that BPS bound. Something we will see later in the context of ADS-CFT. ADS5, so NS4 super Yang Mills famously has many BPS bounds, and there is a way in which you can zoom in on the string that moves on ADS5 plus S5 near such a BPS bound. And if you do that carefully, you get a particular type of non-relativistic string. Hopefully we'll have time to talk about that later. So in condensed matter theory, or when you make approximations in field theory, typically you run into these sorts of things as well. Also in fluid dynamics, you run into non-Lorentzian geometry as soon as you study non-relativistic fluids. You can also make these non-Lorentzian geometries dynamical. So you can have dynamics. Maybe the most well-known example would be things like Horsava-Lifshitz gravity. That can be formulated in this language. Horsava-Lifshitz gravity started out as something that wasn't diffeomorphism covariant completely, but you can reformulate it in a way that is completely diffeomorphism covariant, or invariant in fact, but using geometries that are non-Lorentzian. Chern-Simons theories, things like special theories in 2 dimensions, you can all formulate them in terms of dynamical non-Lorentzian geometries. Then finally, in string theory, you will encounter non-Lorentzian things. For example, if you study things like DLCQ, that's the discrete light cone quantization of a relativistic string. We will discuss this in a minute. This is T-dual to a non-relativistic string, non-relativistic string theory. You will encounter this in the context of dualities. For example, in ADS-CFT. If you approximate a BPS bound. And of course, you can just do plain old approximations of string theory, and then you will encounter them as well. So, of course, once you recognize a certain structure, you start seeing it everywhere. And these are then things that you encounter in theoretical physics really all the time. Once you get the main idea, it's a very basic, simple idea, you will realize that they're really omnipresent. Okay, so let me now give you an example of these boundaries of non-ADS spacetimes, and then slowly I will try to introduce some notation, and I will set up some definitions for these non-Lorentzian geometries. Right, so let's start with something really familiar. So we write ADS in a Poincare patch. There can be many axes, it doesn't really matter what the space-time dimension is. Okay, now it's useful to think of this in terms of Vielbeine. So this will be the normal direction towards the boundary. And here I can write this part here. I will write it as minus E0, E0, plus a number of spatial Vielbeine. And so E0 in this case, I can write it as, say, 1 over r times tau, where in this particular case, tau is just dt. And this one I can write like this. Okay. And if you have asymptotically area spacetimes, all that changes is you get subleading one of the R terms here. But you should think of this now as objects that live on the boundary. So the boundary is at R is 0. That's where you have your Penrose boundary. And you see that, so this is the normal direction. So if I focus on all the other directions, all these Vielbeine, they go as 1 over R. So they blow up at the same rate. And of course, because these are Vielbeine, they are subject to a number of gauge redundancies. So the bulk gauge redundancies are local Lorentz transformations, plus of course diffeos. And these gauge transformations, they have to preserve the boundary conditions. So I can act on these Vielbeine, and then I get something else where maybe I have tau prime and E prime, but it must be 1 over R. And that tells me how the local Lorentz transformations and the bulk diffeomorphism decay as you go to the boundary. And so there is some parameter that are functions of R and boundary coordinates. And these have to decay with R is in such a way that it preserves the boundary conditions. And if you work it out, you get that tau transforms on the local Lorentz transformations. So there will be some parameter that I will call lambda A, which is then the leading order piece inside here that will act like this. You will have some kind of spatial rotations, and something like this will happen. So this is like an SOD, and these are your Lorentz, local Lorentz transformations. And the reason that you get this is because of this fall off here. And so I get a Lorentzian structure on the boundary because I have Vielbeine. They are nowhere vanishing. If I put them in a matrix, that matrix is invertible. And I can build a metric because I have Lorentz transformations. But let's change the metric now. Let's take what is called a Lifshitz spacetime. We put a Z here. And we'll just assume that this is strictly larger than 1. So this is called Lifshitz. So that means that all that will change is that this becomes Z. But because Z is larger than 1, the time-like Vielbein blows up faster than the space-like ones. And that means that this analysis of like what are the allowed bulk transformations that preserve my boundary conditions will change. Yes, very good, thank you. Yeah, I normally put DT first, so that's probably one. Yeah, that should be here. Yeah, thank you very much. This calculation changes. And because the time-like Vielbein is now the dominant one, this term is no longer there. So now you get 0. There are no local Lorentz, it's probably not the right word anymore, transformations that move tau into E. You still have spatial rotations because they all decay at the same rate. Now, depending on circumstances, you may still have this term, but you may not have it. That in order to study that, you have to really do more of full, honest analysis because a Lifshitz geometry doesn't solve vacuum Einstein with a cosmological constant like ADS does. You have to add matter fields, and these matter fields are part of this discussion. And depending on what you choose for the matter fields, this term is either there or it's not there. So this one level just write maybe. This is case dependent whether you have this. But it's clear, because this is 0, you now get something non-Lorentzian. So non-Lorentzian geometry is a geometry that it's a manifold with nowhere vanishing Vielbeine that you can put in a matrix that is invertible, but they don't transform on the local Lorentz, they transform on some other group, often called some kind of structure group or G group. And then the kind of non-Lorentzian geometry depends on what group are you dealing with in every particular case. So another example of this kind of behavior is in the context of flat space. So in that case, yeah. Oh, it's just only these two? Yeah, sure. Then I don't get confused with the different. Oh, this is really racist. So this is readable. You can read this. Yeah, legible. Yeah. So I'll give one more example of this phenomenon where the boundary geometry is not Lorentzian. So Minkowski space, pure Minkowski space, but it works. The argument works for asymptotically flat spaces in general. I'll write it in the following coordinates. This is the metric on a round sphere that is either, well, if this is 4-dimensional, this would be a 2-sphere, or a 3-sphere if it's 5-dimensional, etc. You can recognize that this is Minkowski space simply by saying U is T minus R, and then you get minus dt squared plus flat space in spherical coordinates. Now, we want to use a Vielbein approach. So we're going to write this as minus 2uv. So now I use nullbeine, because clearly this is asking for a nullbein basis. So I will take v to be du, u to be dr plus 1/2 du, and e, I can take it to be r times little e, where little e is a Vielbein for the round, let's say it's a 2-sphere, for the round 2-sphere. And this one, I will just call tau again, just like we did before. And now you go through the same analysis as before. You have Vielbeine, so you have local Lorentz transformations. You have bulk gauge transformations. And you ask, what is the most general such transformation, such that I preserve the boundary condition, where the boundary condition in this case is that this one is order r times whatever. This one is order 1 times whatever. And this one has this structure here. And you can do that, and then you get that the answer is that rather than having what we have here, you get a different answer. Now you get that tau can go into E, but the E's only rotate among themselves. They never transform into tau. And this is what we associate with Carroll. So there's essentially, you can make a little table of what are the options. So let me put some number in front here. And these numbers are either 0 or 1. And then I'll just make a little table for the different options. So if we have a 1 and a 1 in both transformations, so that means I have a 1 here and a 1 here. This will be Lorentzian geometry. If I have 0 here and a 1 here, which we had in the Lifshitz case, then we have something that is, so time does not go into space, but space goes into time. That's something we associate with Galilei structures. I can have it reversed. Time goes into space, but space doesn't go into time. That's something we associate with Carroll. And finally, you can have 0, 0. So that means that there's no boost symmetry of any kind. And I think in the 70s, it was maybe Penrose, for different reasons, classified various kinds of structures on spacetimes, and he coined these types of spacetimes Aristotelian, because Aristotle believed that there was an absolute frame of reference, which is what you would have if you don't have boost symmetry, because then observers that move at constant speed with respect to one another are no longer equivalent. And so the 0 velocity observer is an absolute frame of reference. And so we call these Aristotelian spacetimes. You may find that these are quite exotic, but actually they're very generic. This is the generic case. And the other ones, you can view them as more structure added onto this one. So in condensed matter physics, the Aristotelian case is very common because there's often a kind of medium that interacts with the system you're studying, and that medium breaks boost symmetries. It often also breaks all sorts of other symmetries, but definitely breaks boost symmetries typically. Horsjava-Lifshitz gravity is the dynamics of Aristotelian spacetimes. But these are your four basic options. Yes.
The fact that hello, hi.
Hi.
The fact that for z different than 1, you have delta tau equals 0.
Yeah.
Does this mean that if you compute the algebra of the transformations allowed for general z, there is a discontinuity when you take z close to 1?
You get an enhancement of the algebra, yes. So, yes.
So there is a smooth limit or a contraction type of limit if you take z to 1?
So in terms of, it's not smooth, no.
Okay.
No. And you can also understand this because in order to have z different from 1, you need matter. Whereas the z is one case, cosmological constant is enough. So it's really a different case. Yeah. Other questions? Okay. So these are the four basic options. Now, a lot of people, and you will hear probably more about this in later talks today, and in fact, also if we get to it when we talk about strings, there is a generalization of this because this one are sometimes called particle limits because I treat time different from all of the space, but I treat all space the same way. And you can change that a little bit. You can rescale some of the space along with time and the rest of the space differently. And so there is a generalization where instead of having one tau, you give it an index, where this index transforms under Lorentz or some p. We'll see an example for p is 1 when we do string theory, but I just wanted to mention that you can do these things. So non-Lorentzian geometries are manifolds, and so the physics on it is diffeomorphism covariant, or if it's a dynamical theory, it's invariant. And so they have all of the nice things that you're associated with from GR, but they have a different notion of relativity. So rather than having special relativity in the sense that your light cones at every point are at 45 degrees, now you get light cones that are either, in the Gallet case, your light cone would be this. In the Carroll case, the light cone would be that. This one would be like this one has no light cone. And so in field theory, if you know, how do you see these geometries in field theory? Well, it has to do with the kinetic terms inside a Lagrangian, because that's what tells you about the light cone structure of the theory. So very schematically, you can have field theories that are parametrized. For simplicity, I use scalar fields, but it also works for other spins. But you have some structure like this. There are some couplings, where you only have one time derivative, and then you can have other fields, let me call it BA, B, which are second order in time derivatives. And then there's some gradient terms. And then there is some potential that depends on all these phi's. This is a very generic kind of field theory that you could encounter. Now, if you have no gradient terms, then it's only time derivatives and a potential. That will be Carroll. The other way around, if you don't have time derivatives with only gradient terms, that is a particular instance of Galilei. If you don't have second order time derivatives, only first order time derivatives and gradient terms, that is also Galilei, but in the sense of that's like the Schrödinger equation. And that lives on this Newton-Cartan geometry that we'll talk about in a minute. And then there are many other options possible. So if you couple this now to a curved background, that background would have to be some non-Lorentzian geometry in general. So that's how you see them in field theory, very crudely speaking. Okay. So now I want to focus on a particular type of non-Lorentzian geometries for the rest of this talk that go in this row here. So these are the Gallet case. This is associated with non-relativistic physics because that's what we need later for the string theory case. But before we get there, I want to talk a little bit about 1/c expansions of general relativity. So the way you would set this up is so this is now really different from what we did before, where here we had some coordinates and we zoom in on a particular, so this is basically going down in dimension. So I start with, say, 4 dimensions. I go to the boundary, it becomes 3 dimensions, and I see non-Lorentzian structures. Here we stay, let's say, in 4 dimensions, and I'm going to take an approximation. So what we get out of it is, again, 4 dimensions. So you would parameterize your metric again in terms of Vielbeiner, where I stick in a factor of c under the timelike Vielbeiner. And now I Taylor expand these Vielbeiner in 1/c. And in principle, I should allow for all powers of c, so odd and even. For the purposes of what we are going to do, we will restrict to the even powers, but that is without loss of generality. But that's just for simplicity. The odd powers are actually very important in if you study post-Newtonian approximations of black hole mergers that send out gravitational waves, because they capture radiation retardation effects. I'm leaving them out now just for simplicity, but really they are important. There's lots of physics in them. But okay, so we have spatial Vielbeiner here and corrections like that. Now, because everything is always rotation invariant, it's useful to introduce some notation. So if this object, I will call H. So be careful here, because I have, this is not a square object. I have, say, A is 1, 2, 3, if we're in 4 dimensions, but mu is 0, 1, 2, 3. So correspondingly, this one has signature 0, 1, and then 3 ones. Okay, so it's a degenerate object. You can't invert it. I knew this was going to happen sooner or later. So if you expand the metric this way, then you get minus c squared tau tau plus this h minus plus 1/c squared correction. So I defined for you what h is, and I defined for you what tau is. But because of the c squared here, the term that is subleading here, when you multiply it out, also adds to the order 1 term, which is where h is sitting. And that's where this m is coming from. So I've called the next term here, it's a connection called m that plays a very important role in non-relativistic approximation. This is where the Newtonian potential is hiding. Okay, but this is a very formal thing to do, and you can do this to any order that you like. And now you can expand your favorite Lagrangian using this expansion and see what happens. So if we take, for example, a point particle, or a massive point particle with a world line action like this, and let's say it has a charge as well. This is my massive charged relativistic particle action. Now I want to 1/c expand this, but the variables of the Lagrangian are x, right? this is a thing that depends on x. You vary x, you get Euler-Lagrange equations for x. So once you start expanding, the rule is that you have to expand everything. Otherwise, you get inconsistent equations. So we're going to expand this x, and the leading order will be little x, and then there is a correction, like so. And likewise, this gauge potential, we will say that it goes as c squared. These are choices, because you may wonder, why did you decide to put c squared here and 1 here? There's not a unique way of doing it, but there's often 1 or 2 ways that give you interesting physics, and the other ways don't give you interesting physics. But there is no algorithm that tells you you have to do it this way and no other way is allowed. So there are choices, different approximations, basically. Okay, if you do the calculation now, you know how to expand this, you know how to expand this, you know how to expand this. Then this Lagrangian, in general, will have a c squared term, and then I'll call that the leading order Lagrangian. And then you get the next to leading order Lagrangian, which is order c to the 0. And then it basically, you get a cascade of Lagrangians. And you should think of this as a better and better and better approximation of the relativistic theory. There is a certain well-defined way in which the most subleading Lagrangian that you focus on knows all about what happened before. So you can prove that the equations of motion of the leading order Lagrangian are reproduced here by the more subleading fields, and then you get additional equations for the extra field that you've introduced, and this repeats itself over and over again. Now, yeah. Yes, exactly. Yeah, exactly. Now, there's now a very important choice that you can make. You don't have to, but and this divides the literature a little bit in some sense, because you could say I just do the most general 1/c expansion, and I just accept what I get out of that, and I just view it as an approximation, really. That's the post-Newtonian viewpoint, and it's a very valid viewpoint. But you can also say I'm interested in limits. I want to send c to infinity and get rid of it altogether. And then this is a problem because this blows up with c squared. So there is a choice where some people set this to 0 by hand. And what that means is that, and here it's important that the particle has charge. If it's a BPS relation, so the charge equals the mass in a certain way, you can make it 0. So that's what happens when you zoom into BPS bounds. The BPS bound in this case will set the leading order Lagrangian to 0, and then the limit will just give you this. This is then your limit theory, which is kind of a decoupling theory. And this is what happens, for example, in string theory, as we will see later. But this is a choice. You don't have to do that. So if you go for this option, then what you're saying is that this one, so Q times A minus 2 is the mass times the time-like Vielbein at leading order. I can just fix it this way. And that basically means that my electric field at leading, well, no, I should say that the gauge potential at leading order is electric with a charge equal to mass. That's how you should view this statement. And that's exactly what gives you the BPS relation. And then if you do that, then this next to leading order theory describes a non-relativistic particle with a non-relativistic dispersion that couples to Newtonian's potential, which is sitting inside of this field here. So you should think of M as a sort of the gravitational analog of A, because here you would have the Coulomb potential in the time component, here you have Newton's potential in the time component. But there's one very important difference. This one is Lorentz invariant, or yeah, because this is a Lorentzian theory, so this is the right thing to say. So this is Lorentz invariant. This is not invariant under the Galilei transformations, which are the equivalent of the Lorentz transformations in the non-relativity regime. So this has non-trivial transformations on the Galilei transformations. And the reason you can see that is because this one, under a Galilei boost, goes into tau, as we've seen before. So to compensate for that, in order for this to be invariant, this compensates for that by going into E under a Galilei boost. And that's really what makes Newtonian gravity so different from Maxwell's theory. Okay. Now, one more comment about this before we turn to the string theory case. Right, can remove this. So we have expanded the particle action, but you can, of course, expand the Einstein-Hilbert action and see what you get. And if we throw in a cosmological constant, and you would get something like this. And you expand this out, and then it's just a matter of calculation. You get the leading order piece is c to the 6. Then you get some leading order Lagrangian, a next to leading order Lagrangian. And because this one is very interesting, there's also a next to leading order Lagrangian, etc. You get a cascade of Lagrangians, and like I said before, the equations of motion of this one reproduces the equations of motion of that one, plus new equations of motions for the new fields. And that is always the case. You can prove that on general grounds. Now, this theory contains Newtonian gravity. But it contains more than that. And there's a very interesting interplay between what happens with this theory and what happens with the matter that you add to this expansion. I'll explain why. This one, at order c to the 6th, is never sourced by any matter, because you can argue that the expansion of the matter Lagrangians are at most c to the 4th. And so this one is never sourced by anything. And it really just puts a constraint on the geometry. It tells you that tau, wedge d tau, is always 0. Which is the Frobenius integrability condition for saying that tau is hypersurface orthogonal. So this is equivalent to saying there are two scalars, let's call them n and t, such that you have this. So t is not a coordinate, it's some kind of time function on the manifold, and constant t slice the whole manifold globally well-defined way. In Horsava-Lipschitz gravity, you would do exactly this thing. That's what gives the foliation structure. And so the non-relativistic theory always gives you this kind of foliation of time. And it's kind of a causal condition that this is kind of Galilean causality. You can show that that is the case. Now, what happens here depends on the matter. And let's, for the moment, view the cosmological constant as a kind of matter. So this cosmological constant is just a parameter, and I have to choose how it scales with 1 over c. And there are choices that you can make. One choice is to say it goes to order 1. If I do that, it will source this theory here. So if the cosmological constant is order 1, it will source this theory here. And that has very interesting solutions, like the non-relativistic equivalent of ADS, if the cosmological constant is negative, is a solution of that theory. And that is a space-time that has a boundary, which is like a Newton-Cartan boundary of a Newton-Cartan geometry. And you can then imagine that this is a nice setting for some kind of non-relativistic holography, where the bulk is not described by Einstein gravity, but by some non-relativistic theory of gravity. You can also make the choice that it goes as 1 over c squared, in which case it starts sourcing this theory for the first time. So then it doesn't source this theory. And if you do it that way, you can show that if you do it this way, you get that tau is just dt. So you get an even bigger constraint, not just n, where n is any function dt, but really it's exact. And this is absolute time in the Newtonian sense. So that's the real sort of Newtonian universe. Whether you get a real Newtonian universe or something slightly different depends on what kind of matter you add to your theory. So if you take the particle action, you see it started at order c squared. It sources this theory. So a massive particle sources the next to leading order theory. It doesn't source that theory. that means that if I take this 1/c expansion of the massive particle, it will give me a Newtonian universe, and I will get honest Newtonian gravity, as I get an action principle for Newtonian gravity. If I take some kind of different matter, so not this particular action, but something else, where this starts at order c to the fourth, I will start sourcing this function n. And you can therefore have gravitational time dilation in a non-relativistic setting. This is a real thing that can happen depending on the matter that you put in. So the matter decides whether you have a Newtonian universe or you have already some kind of gravitational time dilation in your theory. Yeah. Yeah.
There is also another scenario where it could be larger when you take like order c to the power 2.
Oh, plus c squared, you mean?
Yeah, in that case, it would source the lead order and would modify your continuous.
Yeah, but then you violate causality. Yeah, so it's not a, it doesn't become a good theory at that point. Yeah. Any questions about this? So one of the reasons, and this will be the last comment before we move to strings, one of the reasons I'm particularly interested in this theory is that it's an interesting theory that you can study on its own merit. It contains Newtonian gravity, but as I said, it's richer than that. It can also capture tau's where n is not constant. And there's some interesting questions that you can ask. For example, if I take the Schrödinger equation for ordinary quantum mechanics, I know how to put it on a curved background. The Schrödinger equation is invariant on the Galilei symmetries. If you gauge these Galilei symmetries, you get Newton-Cartan geometry. And so the Schrödinger equation couples to Newton-Cartan geometry. And in fact, it back reacts. So how do you treat that quantum mechanically consistently? I think it's a very interesting question to ask, and I don't think we have a good answer. And I would call that the problem of what you call the non-relativistic quantum gravity, or whatever name you want to use for this. So this would be Newtonian gravity back reacting with a quantum mechanical system in a consistently quantum mechanical way as a theory on its own. And you could, for example, ask, is such a setting a limit of string theory or not? And that's one of the motivations why I was originally interested in studying non-relativistic strings. So let's move on to that. And before I do that, let me ask, how am I doing with time? Ooh, I'm going way slower then, but that's fine, that's fine. Thank you. Okay. That means that we'll be very schematic about the string part as well. So non-relativistic strings, and just for clarity, and now also really because of time limitations, we'll do bosonic strings, and we'll only take closed strings, so closed and bosonic. It doesn't really matter. The supersymmetric and the open cases are just more I mean, the ideas behind them are exactly the same. You just have a little bit more complications. The basic setting, so now we have 26-dimensional space. How much? Yeah. Oh, perfect. Okay, great. No, that's all right. Thank you. Okay, so this is a 24-dimensional vector. And then this is my time. And I single out one direction here. And I'm going to do that because this one is going to be compact. So it has some radius RV. So V will be a spatial circle. And you see I've done something different from what we did before. You still have it here. Here I singled out c squared. I singled out the time direction in a covariant way with a factor of c, but all the spaces were down by a factor of c here. But I've done something different. I've put one of the space directions in front of c squared. So this scales with t. So you could say that only the transverse directions of the string are being treated non-relativistically, and the longitudinal directions of the string are still treated relativistically. But if I pull out a factor of c, I still want this to have the dimensions of length. I need another something speed, which I call c twiddle here, just on dimensional grounds. But for the moment, you can think of c twiddle as this being 1 in some units. But later, if we have time, I will say something about what happens when you take this to infinity. But this is like a two-dimensional. You have like a 1 plus 1 dimensional Minkowski submanifold subspace. And that is because in the first instance, so there's many different notions of non-relativistic string, but the most well-known one still has a CFT on its worldsheet. And so the string equations of motion are embedding maps into a target space. For these maps to be not singular, if the worldsheet is a Lorentzian geometry, it has to map into a Lorentzian geometry in the target. So it will only work if there is at least a 1 plus 1 dimensional Minkowski subspace in my target. But we're going to send C to infinity, so they will kind of decouple a little bit. But this is the basic setting. We need this to be compact because in order to define a non-relativistic limit, you need the object has to have a very large rest mass compared to its transverse motion. And in order to give this string a large rest mass, you let it wind the circle. So we're going to have non-zero winding. So the string has a non-zero winding along the v direction that generates mass with respect to which, with respect to which we will then treat the rest of the spectrum non-relativistically. So if you write the spectrum of the string and you solve for the energy, then because the mass dominates, you can take it out of the square root, and then you can expand the square root in 1 over c. Well, it still has oscillations in this direction. It can definitely move in this direction, but it always has the pullback map from here to the worldsheet is invertible. Yeah. So we call this the longitudinal space, it's a transfer space. But it moves freely throughout the whole space-time. It's not fixed in any sense. Now, just as what you did with the particle, you can ask for a BPS bound. Now, we can just, in this case, you would add a Kalb-Ramond-2 form, and this is called a critical B field. And you can take it to be ETdV with a constant, but this is not pure gauge because V is a circle, so it is only locally pure gauge, but you can't get rid of this. It has a vanishing field strength, but it is not a pure gauge object, so it's non-trivial to do this. And then just for completeness, you can also take a constant dilaton like this. Now, this is kind of the basic setting of non-relativistic string theory. Now, there's a very interesting observation that I learned from Truls Harmark, is that you can now do a T-duality, because this is a spatial circle. You can T-dualize this in the presence of a critical B field, and then you get something interesting. So if you just apply the Busher rules along V, then you get a new background where there is no B field, there is no dilaton, and the metric now takes the following form. dt du plus c twiddle over c squared du squared, and then all your x's. Now, if you now send c to infinity, where of course the t-dual direction is u, right? So u is compact with some radius, some inverse radius of the other one. If you now send c to infinity, then this term clearly goes to 0, and u becomes null. But it's compact. It's a compact null direction. This is what people call discrete light cone quantization. And that's the old-fashioned way of doing non-relativistic approximations of string theory. And the modern way of thinking is that, because obviously, if I just do this and I take this limit, things become a little bit hairy because you have to work with null circles, and it's of course not very nice. So the modern way of thinking is that really you should do a t-duality first, and then treat it as a non-relativistic string theory by sending this to infinity as well, which we're going to do next. Okay. So let's take the Polyakov action and expand it out in 1 over C for this particular target space. So there's some tension T. My worldsheet coordinates are dimensionless. There's a worldsheet metric gamma. I will call eta my target space metric. So eta is all of this thing here. And then I just have the pullback maps. And then I'll just plus the B field coupling term, but I will not write it out. So just as with the particle case, if you want to 1 over C expand this, you have to 1 over C expand everything that you can vary in your action. So there's 2 objects that you vary. There's the gamma and there's X. So with the X, you do the same as in the particle case. You expand it like this. And your gamma is expanded in this way. This is gamma 2, where we assume that the leading order gamma is also Lorentzian. And that is because in this type of non-relativistic string, the worldsheet is still described by a Lorentzian geometry, and it has this particular metric. Okay, thank you. So if you do this calculation, you just throw it in here. You take this critical B field. What the critical B field does for you is that what would be there at order C squared cancels out. And then you're left with a theory that is just finite, and you can send C to infinity and get a finite theory. And if you do that, you get what is called the Gomez-Oguri string. And let me write down the action. At least you have seen the action. So you have to make a choice about the tension. So we'll just say that C times T is C twiddle times a non-relativistic tension. And then you get T twiddle, T non-relativistic over 2. And now you get gamma 0. And importantly, you only get the transverse directions here. And then you get 2 more terms, which are Lagrange multipliers. E plus is because this is Lorentzian, I can decompose it into worldsheet Vielbeiner. And E plus is one particular null version of this worldsheet Vielbeiner. X plus is a particular combination of xt and xv. So these are the embedding coordinates for these coordinates here. And there is a similar one where you interchange the plus and the minus. And this lambda is a Lagrange multiplier that comes from this term here. So the subleading part of the worldsheet metric becomes a Lagrange multiplier. And this Lagrange multiplier forces in a way that this string always, the string, think of the string as a closed string, so the worldsheet is a cylinder, and these Lagrange multipliers make sure that that cylinder always maps into what is, this is also a cylinder, so this is a cylinder mapping to a cylinder, and that transformation is always invertible. That's what these Lagrange multipliers do for you. Now you can do this also for open strings, and then you can show, I'm not going to write any equations, but I'll just tell you what happens. So if you do it for open strings, then the endpoint of the string For example, it ends on the D24 brane. The circle that the string is wrapping is in the transverse direction, so it gives you the mass. And then the relativistic string that ends on the D24 brane is a massive particle. So the endpoint is the 1/c expansion of a massive particle that becomes a non-relativistic particle. You can give it charge, then that non-relativistic particle sources some kind of electrodynamics. But the geometry on the D24 brane is not relativistic. It's some kind of Newton-Cartan geometry. So you get some kind of non-relativistic Maxwell theory. And it's not hard to figure out what particular Maxwell theory you get, because there is one scalar for the transverse oscillation of the D24 brane, and you have a gauge field on the D24 brane. And the theory you get is some nonlinear version, some Born-Infeld version of what we call Galilean electrodynamics. But I will skip the details of that. So the last comment I make, and then I will end, is I wanted to make contact with BPS bounds in ADS-CFT. And for the interest in time, I will just say the words. So I have carefully kept track of this C twiddle. And what you can do with C twiddle is that you can take a further limit by sending C twiddle to infinity. And if you send C twiddle to infinity, and I generalize this a little bit, because here I couple to a flat background, but I can easily put in some kind of metric here. And I can send C twiddle to infinity in a particular way that I get a finite answer. Then I will just write the result that you can get. So you have to do you have to make a couple of choices. So you put in an arbitrary metric for the transverse directions, and you allow for, you have a critical B field, but then you have also a subleading B field that is chosen in a particular way. All that can be made very well defined, but then you get an action that is quite interesting with a tension I'll call T prime. And then you get, this is kind of a Nambu-Goto version. This is a dot, so this is a worldsheet time derivative. I'll just be very schematic here. You get this kind of theory. So you see, it's first order in time derivatives. So you get a two-dimensional sigma model that's first order in time derivatives and second order in space derivatives. And if you make appropriate choices for M and H, this captures things like the continuum limit of the Heisenberg spin chain, for example. So if you take, for example, if I take H to be the metric on the two-sphere and M to be something like cosine theta d theta, then this is the continuum limit of the Heisenberg spin chain. And what is really interesting is that, and we know that this is associated with the SU2 sector of NS4 super Young Mills. There's a quarter BPS bound, and you can, the one loop dilatation operator just close to that bound is exactly this Heisenberg spin chain. And the string theory, if I take strings in ADS5 cross S5 and I take a particular limit, there's a certain dual description for what this limit means, that string theory becomes exactly this Lagrangian. And so the Heisenberg spin chain has a string theory interpretation, not in terms of the Gomez-Ooguri string, but as a limit of the Gomez-Ooguri string, where I take this C twiddle to infinity. So, and this is actually true for all the BPS bounds of NS4 super Young Mills. You just get different versions of M and H, depending on which BPS bound you zoom into. And this is called the, and that's the last thing I'll mention, this is known as the spin matrix limit of NS4 super Young Mills. So this gives you spin matrix theory. And this spin matrix theory is very interesting because it's defined at finite color. I don't have to send, you can define the limit on the field theory side at finite color. Of course, on the string side, that's very difficult, but on the field theory side, you can do it at finite color. And so it's a very interesting limit to study, and you get a non-relativistic dual theory. And so this is one particular version of, say, non-relativistic holography, where you have a non-relativistic limit of NS4 super-Yang-Mills being dual to a particular class of non-relativistic strings. All right, I'll end there. Thank you very much.
So questions, please.
Is this on? Yeah, very good. Thank you for a very nice introduction. I was wondering if because there seems to be a very good handle on these non-relativistic geometries.
Yeah.
Because I come from supergravity, I would be interested if there's also good handle on spinors over these geometries.
I think your answer is going to be answered. Your question is going to be answered in some of the later talks today, I think. Of course, not sure what they will talk about. But the short answer is yes. People have studied non-relativistic supergravity theories. I mean, Jan Rosil is a big expert on that. People have studied, what has been done more, I would say, is study the bosonic sector of supergravity theories and take various non-relativistic, put them on different non-relativistic geometries. Because they have all sorts of p-forms, you have to think very carefully about how you treat these p-forms. As you send C to infinity, so they have to scale with C a certain way, and that leads to E-brane, Newton-Cartan geometries, and all these words that are associated, or the Carolian version of that. Really, with spinners, I think maybe a little less work has been done. Also on the superstring side, I think there is room for more work because it's just more difficult, obviously. But I think people know how to. It's known what representations are of the various non-relativistic groups in terms of spinners.
Thank you.
What happens if you take this limit with the Virasoro amplitude with observables?
So in this paper by Gomez Oguri, they looked at scattering of the, say, well, it's a bit tricky to call it tachyonic state, but let me call it that anyway, because that would refer to a Poincare representations. In this case, of course, they're representations of some non-relativistic target space group. But what you get is that you can have these so 4 external states. They scatter, and the interactions are instantaneous. So what you would normally call the massless sector, which isn't okay, let me answer the question as follows. There's no non-relativistic version of a graviton. So that means that the external states cannot be gravitons. But there are still, and that's what I was alluding to when I was talking about the 1/c expansion of GR, you still have Newtonian potentials and other instantaneous corrections to that. And they can propagate inside loops. So they're still able to produce interactions, but they can't live, you can't detect them. So, so you can definitely have scattering that leads to some kind of Newtonian interaction between these external states that is mediated by, you can write down vertex operators for what you would normally call the graviton.
I'm not sure I understood the answer. So if I consider just scattering of gravitons, say in type 2A or type 2B superstring theory, no tachyon, right? Everything.
No, okay, but this is bosonic string theory.
Yeah, I understand. I'm just asking a bit more general question. So then I have a well-defined expression, well-defined amplitude. And the question is, what happens with this amplitude if I take your limit?
Okay, I understand. Yeah, so Well, so I don't know if that calculation has been done. I mean, like I said, there are not going to be, the equivalent of the graviton will not exist if once you take the limit, because these are, yeah, these are not the particles that are detectable. So you can, the representation theory is a little bit different because you have now states with zero momentum, I think. And you have to account, so they have non-zero energy but zero momentum, so they're a bit strange. And this is what you would call maybe a non-relativistic graviton, but they can, so it could be that the answer is if you just take that calculation in isolation, maybe you get rubbish if you take the limit. But you should be careful because the limit doesn't necessarily commute with quantization. So you have to, it's what you mean by the non-relativistic quantum theory, you have to be quite careful when you start quantizing and when you take the limit, because these things don't commute. So, so I haven't done the calculation. It would be an interesting thing to do. And the calculation that has been done is that you can get instantaneous interactions between different external states. I don't know if that answers the question, but.
Thank you.
One way to construct shockwave geometries in relativistic gravity is to boost to the speed of light. Start, let's say, from Schwarzschild, do some boosting between time and one space parameter, and then, if you are careful, get some shockwave geometry. In the non-relativistic limit that you take, I guess that boosting is not allowed. So does this imply that we don't have shock waves geometries in non-relativistic theories?
That's what I would expect. Yeah, I think that's correct.
Thank you.
Could you elaborate a little bit more about how Born-Infeld theory arises in this non-Lorentzian regime?
Sure,
Or
yeah.
give
So
some reference.
reference, well, yeah. Well, yeah, okay. So I think maybe there's a review paper by Gerben Oling and Ziki Jan where I think they talk about it already. I also have a paper which is called Non-Relativistic Approximations of Open Strings, where we also derive it. The way that you would get this is you take the standard Born-Infeld. So let me write one equation. So if you take for a D24 brane, in static gauge already, so I have some brane tension and then some coordinates here. And this is in a background with a critical B field. That's very important in order to get this answer. And then you have the 1 over C, so I'll tell you what M is in a minute. So mu, if I take I take the same flat geometry with a circle that we had before, then this would just be eta mu nu plus your critical B field plus some world volume gauge field. And then the coordinate xv, the transverse one, you're going to replace this with your xv plus some kind of transverse scalar field that depends on the world volume coordinates. And then you plug it all in here. And then if you then expand for small tension, this is the string tension, right? It's not the brane tension. So this would be C twiddle times the non-relativistic tension. If I work to order 1 over T squared at that order, rather than getting, if you would do this in the relativistic case, you would just get Maxwell plus the action of a free relativistic scalar. In this case, you get this theory of Galilean electrodynamics that some people call GED. give you more details offline, but that's roughly the calculation that you have to do.